Okay, today we're looking at the 2018 investigative task, which is a sixth question on the stats exam. All right, here we go. The systolic blood pressure is the amount of pressure the blood exerts on blood vessels where the heart is beating. The mean SBP for people in the U.S. is 122 mmHg, standard deviation of 15 millimeters mercury. The wellness department investigating whether the mean SBP is greater than the reported national mean. So 100 employee sample. Okay, they define mu for us. They say it's the mean systolic blood pressure of all employees of the corporation. Consider the following hypotheses. The H naught mu is equal to the national mean, where they think mu is greater. Okay, cool. Describe a type 2 error in the context of the hypothesis test. Okay. So a type 2 error, we can say this. Type 2 error. It's basically that the H alternate is true, but the null was failed to be rejected. Doesn't make sense grammatically, but there you go. So now we got to put that in context. So you can basically say the type 2 error here would be how, or not how, if would be if the mu, because they define mu, is actually greater than the national average of 122 millimeters of mercury, but the null hypothesis was not rejected. It was not rejected, and mu was stated to be equal to 122. That's part A done. Now let's look at the next part, part B. Assume that sigma is 15 millimeters of mercury. If mu equals 122, the sampling distribution of x bar for samples of size 100 is approximately normal, with a mean of 122 millimeters of mercury, standard deviation 1.5. What values of x would represent sufficient evidence to reject the null hypothesis at the significant level of alpha equals 0.05? Okay, so there's a trick to this question, and it's simply that. So this alpha of 0.05, this is basically 5%. So we can draw a standard deviation curve. Okay, and we know that this is the bottom 5%. This is what alpha basically represents. This is the bottom 5%. This is the top 5%. This middle range, this is your confidence level. This is your 90% confidence level. So this is actually how you determine your z-score. Because this question is just simply a z-score. So if we head over here, grab our highlighter. Okay, for some reason it won't. Okay, basically, oh, there we go, right here, 90% is our confidence level, and this is z, or no, this is means, but we're gonna use the infinity row. This is means, we're using the infinity row. Here we go, here we go, here we go. 1.645. Okay, cool. That's our z-score for a 90% confidence level. It would be equal to 1.645. So we know that z, oh, yeah, this is b, by the way. We know that z is equal to x bar minus mu over the standard deviation, and standard deviation is defined. So what we don't know, we want to find the minimum x bar that would allow us to present the significant evidence. That's why we're going with a 90% confidence level, as we found with the alpha of 0.05. So 1.645 should be less than x bar minus 122 over 1.5. When you do the cross multiplication and you solve for x bar, you get x bar to equal 124.4675 millimeters of mercury. So that's the minimum. That's the minimum x bar that would represent sufficient evidence to reject the null hypothesis at a confidence level of 90% or at a significance level of 0.05. Okay, cool. Now we can move on to part C. Oh yeah, make sure you're giving sufficient context. Make sure you're showing your thought process so that they actually understand what you're doing. So that's very important. Because otherwise, if you like, let's say you screw something up, they won't be able to give you partial credit if you don't show any work, obviously. All right. The actual mean systolic blood pressure of all employees at the corporation is so okay. They're telling us the true. They're telling us that the true is 120. The true mu is 125 millimeter mercury, not the hypothesized value of 122. So it's actually 125, not 122. Okay. But the standard deviation is the same. Okay. Using the actual mean of 125 and the results from Part B, determine the probability that the null hypothesis will be rejected. Okay, so the easiest way to go about Part C and to guarantee you get the credit is to realize that this is just another z-score question. So z is equal to x bar minus mu over standard deviation, which is equal to x bar, which we defined up there, or we found up there to be 124.4675. Our mu is 125. Our standard deviation is 15 divided by the square root of 100. Because remember, we're not changing the sample size. All that we know is that we have a different x bar. And this is the standard deviation for a sampling distribution with an n of 100. So now this is going to equal negative 0.33, or 355, not 335. 3 negative 0.355. Okay, so this is our z value. The z is equal to negative 0.355. Well, on your reference table, you'll find a table with this curve right here. It's a standard normal bell curve, and you're given a list of z's and the z by z, and then the p-values is all this. So we're at negative. Let me get my highlighter. We're at negative 0.3, and we're right in between 0.05 and 0.06. We're right down here. That's very straight. Nice. Alright. Okay. So when this happens, you have to just take the average of the two that is in between. I'll show you what that means. So 0.3632 plus 0.3594 divided by 2 is equal to, grab a calculator. 0.3632 divided by 0.3, or plus 0.3594 divided by 2 is equal to 0.3613. Equal to 0.3613. Okay. Well, this actually isn't the whole part of the question. This is that this is for everything below, but I believe we wanted the values above. Let's see. Oh, whoops. Yeah, we wanted so negative 0.355, and the question was asking um, determine the probability that the null hypothesis will be rejected. So the p-value, okay, the power. So we got our z to be negative 0.355, and we found that the probability that x or um, that what is it? Z was less than or equal to negative 0.355 is equal to 0.36. But we wanted everything above that. We didn't want everything below. So all we have to just do, we have to subtract this probability from 1 because all probabilities add to 1. So 1 minus 0.36 will equal the probability that Z is greater than negative 0.355, which is going to equal 0.64. There you go. Make sure you're using accurate notation. Otherwise, they might not give you credit if you're using incorrect notation. Okay, so now part C. It says what statistical term is used for probability found in part C? Well, in part C, it's the probability that the null hypothesis will be rejected. Well, this is the power of the test. So this is something that you just had to know. The probability of rejecting the null hypothesis, so D, the probability of rejecting the null is known as the power of the test. There you go. That's part D done. That that was very nice, if you knew it, of course. Okay, now part E. Suppose the size of the sample of employees is selected is greater than 100. Would the probability of rejecting the null hypothesis be greater than, less than, or equal to the probability calculated in part C? Explain your reasoning. Okay, well, there's a simple relationship that we learned in class. We learned that power, or the probability of rejecting H naught is affected by a few things. So affected by 1. It's affected by sample size. I'm just going to sample size, sample size, or N, and 2, alpha / confidence level. So the effect is that a large N, a large power. Then a large alpha, therefore small confidence level, equals large power. So I believe part E was saying how they wanted to make the sample size greater than 100, yes. So simply state, because the N, or sample size, is being increased, and there is a direct relationship between N and power, and then say parentheses, probability of rejecting H naught. Make sure that's neat, because Let me just fix that because you don't want to lose credit for not being neat. H not between n and power. So because the n or sample size is being increased, and there's a direct relationship between n and power, the probability of rejecting null, increasing n increases the power, or probability of rejecting the null, because that's how they word it in the question. You always want to word it in the way they do. Now another little trick is to realize this. All they're doing is changing the sample size. So this 1.645 needs to say constant, right? Then I believe this 1.5, for example, let's test this out. We know that it's 15 divided by square root of 10. Sorry, 15 divided by the square root of 100 is 1.5. So what if we increase the sample size now to another perfect square to make this easy, 400? It becomes 0.75. So now it's 1.645 is less than x bar minus 122 over 0.75. Well, 1.645 times 0.75 is that, and plus 122 is 123.23375. So now your x bar with a lower standard deviation is less than with a larger standard deviation. And that basically means that your H naught is incorrect. You've increased your probability of rejecting the null. Another way to think about it is that with a larger n, with more data, you're likely to get a more accurate or correct proper sampling from more data. As always that happens, like law of large counts. So the probability of rejecting the null, if the null was wrong, would therefore be increased. So the easiest way to explain it is this: the direct relationship um, between the sample size and power. But if you get confused, like, you can just think, like, they give you a lot of clues, a lot of context clues, and you can make a lot. I mean, after all, this is inferencing. You can infer with like, obviously with a degree of reasoning. You can reason things out and still get some credit. Like, um, giving an explanation of X bar and affecting that might not be what they wanted, but you could still get some credit as opposed to just leaving it blank or taking a wild guess. So as long as you know that there's a relationship between n and sample size, no, sample size and power, then you were good to answer this question. And there you go. This would give you full credit. Um, all this work will give you full credit for this investigative task. All right. Thank you.